When examining a one-line electrical schematic, annotations such as 2-1/C-500 KCMIL per phase indicates a parallel feed. The number preceding the dash, in this instance the number 2, signifies that it is indeed a parallel feed. Conversely, if that number were the number 1, it would denote a single conductor feed rather than a parallel configuration. The designation 1/C stands for one conductor. This indicates the number of conductors per phase within the parallel feed. In the example notation 2-1/C-500 KCMIL per phase, the number 2 at the beginning indicates that there are 2 such conductors per phase run in parallel. The value following the 1/C, which is 500 KCMIL in this example, specifies the size of each individual conductor. KCMIL represents 1000 circular mils, a unit of measure for the cross-sectional area of the conductor. In summary, the notation 2-1/C-500 KCMIL per phase communicates that there are 2 parallel runs, with each run consisting of one 500 KCMIL conductor for each phase. Let's delve deeper into the concepts of parallel conductors in electrical systems. Using parallel conductors involves connecting 2 or more conductors per phase or neutral to increase the current carrying capacity of a circuit. This is often necessary when the required current exceeds the ampacity of a single conductor. The National Electrical Code, or NEC, provides guidelines for the use of parallel conductors to ensure safety and proper installation. According to the NEC, conductors can be run in parallel if they meet certain conditions outlined in section 310.10. Firstly, all parallel conductors must be the same length. This ensures that the impedance of each conductor is equal, preventing unequal current distribution. Secondly, parallel conductors must have the same conductor material. For instance, you can't run copper conductors in parallel with aluminum conductors. Thirdly, parallel conductors must be the same size in circular mils. The size is typically expressed in American wire gauge, or OG, or KCMIL. Fourthly, parallel conductors must have the same insulation type. This is important for maintaining consistent insulation properties and temperature ratings. Fifthly, all parallel conductors must be terminated in the same manner. This means using the same type of connectors and ensuring proper torque and termination techniques. The advantages of using parallel conductors include increased ampacity, reduced voltage drop, and improved system reliability. By dividing the current among multiple conductors, the overall current density in each conductor is reduced, which lowers the operating temperature and extends the lifespan of the insulation. Furthermore, parallel conductors can provide a redundant path for current flow, increasing system reliability. If one conductor fails, the remaining conductors can continue to carry the load, preventing a complete circuit interruption. However, there are also some disadvantages to using parallel conductors. The installation of parallel conductors can be more complex and time-consuming compared to using a single conductor. It requires careful attention to detail to ensure that all conductors are properly sized, terminated, and supported. Additionally, parallel conductors can increase the overall cost of the installation due to the increased material and labor requirement. When designing a parallel conductor system, it's important to calculate the required ampacity of each conductor. The total current of the circuit must be divided equally among the parallel conductors. The ampacity of each conductor must be at least equal to the calculated current. The NEC provides ampacity tables in section 310.15 that can be used to determine the allowable ampacity of conductors based on their size, insulation type, and installation conditions. In addition to ampacity, it's also important to consider voltage drop in parallel conductor systems. Voltage drop is the reduction in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment malfunction, reduce efficiency, and increase energy consumption. The NEC recommends limiting voltage drop to a maximum of 5% for feeders and branch circuits. To minimize voltage drop in parallel conductor systems, it's important to use conductors that are adequately sized for the length of the run and the amount of current being carried. In addition to the general requirements for parallel conductors, the NEC also provides specific rules for certain applications. For example, Section 392.80 covers the use of parallel conductors in cable trays. This section requires that the conductors be installed in a manner that prevents them from overheating or becoming damaged. It's important to consult the NEC and other relevant standards and guidelines when designing and installing parallel conductor systems to ensure compliance with all applicable requirements. Proper design, installation, and maintenance of parallel conductor systems are essential for ensuring the safety, reliability, and efficiency of electrical power distribution. Let's further discuss conductor sizing and ampacity calculations. Conductor sizing is a critical aspect of electrical design, ensuring that conductors can safely carry the intended current without overheating or causing excessive voltage drop. The ampacity of a conductor refers to its current carrying capacity, which is the maximum amount of current it can continuously carry under specific conditions without exceeding its temperature rating. The National Electrical Code, or NEC, provides detailed guidelines and tables for determining the ampacity of conductors based on their size, insulation type, and installation conditions. These tables take into account factors such as ambient temperature, the number of conductors in a raceway or cable, and the presence of other heat-generating equipment. To determine the appropriate conductor size for a given application, it's necessary to calculate the load current and apply any applicable directing factors. The load current is the amount of current that the circuit is expected to carry under normal operating conditions. Directing factors are adjustments to the ampacity of a conductor to account for conditions that can increase its operating temperature, such as high ambient temperatures or multiple conductors bundled together. The NEC specifies directing factors for various conditions in section 310.15. For example, if a conductor is installed in an ambient temperature higher than 30 degrees Celsius or 86 degrees Fahrenheit, its ampacity must be derated by a certain percentage, as specified in Table 310.15 bone. Similarly, if multiple conductors are installed in the same raceway or cable, their ampacity must be derated according to Table 310.15 B3. After calculating the derated ampacity of the conductor, it's necessary to select a conductor size that has an ampacity equal to or greater than the calculated value. The NEC provides ampacity tables in section 310.15 that list the ampacities of various conductor sizes based on their insulation type and temperature rating. For example, Table 310.15 B16 lists the allowable ampacities of insulated conductors rated up to 600 volts. When selecting a conductor size, it's also important to consider voltage drop. Voltage drop is the reduction in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment malfunction, reduce efficiency, and increase energy consumption. The NEC recommends limiting voltage drop to a maximum of 5% for feeders and branch circuits. To minimize voltage drop, it's important to use conductors that are adequately sized for the length of the run and the amount of current being carried. The voltage drop can be calculated using Ohm's law, which states that voltage drop is equal to the current multiplied by the resistance of the conductor. The resistance of a conductor depends on its material, size, and length. The NEC provides tables that list the resistance of various conductor sizes in Chapter 9. In addition to the general requirements for conductor sizing and ampacity, the NEC also provides specific rules for certain applications. For example, Section 430.22 covers the sizing of conductors for motor circuits. This section requires that the conductors be sized to carry at least 125% of the motor's full load current rating. This is to account for the fact that motors can draw significantly more current during starting and acceleration. It's important to consult the NEC and other relevant standards and guidelines when sizing conductors to ensure compliance with all applicable requirements. Proper conductor sizing is essential for ensuring the safety, reliability, and efficiency of electrical systems. Insufficiently sized conductors can overheat, leading to insulation damage, fire hazards, and equipment malfunction. Oversized conductors, on the other hand, can increase the cost of the installation and may not provide any significant benefit. Let's explore the topic of electrical schematics in greater detail. Electrical schematics are essential tools for electrical engineers, technicians, and electricians. They provide a graphical representation of an electrical circuit or system showing the components, connections, and functions. Schematics are used for designing, analyzing, troubleshooting, and maintaining electrical equipment and systems. There are several types of electrical schematics, each with its own purpose and level of detail. A single line diagram, or one-line diagram, is a simplified representation of a power system showing the major components and connections. It is typically used for analyzing power flow, voltage regulation, and system protection. A wiring diagram shows the physical connections between components, including wire sizes, colors, and terminal locations. It is used for installing and troubleshooting electrical wiring. A ladder diagram, also known as a relay logic diagram, is a specialized type of schematic used for representing control circuits. It shows the sequence of operations and the relationships between inputs and outputs. A block diagram is a high-level representation of a system, showing the major functional blocks and their interconnections. It is used for understanding the overall system architecture and signal flow. Electrical schematics use a variety of symbols to represent different components and devices. These symbols are standardized by organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the American National Standards Institute, or ANSI. Some common schematic symbols include resistors, capacitors, inductors, transformers, switches, relays, and motors. It's important to be familiar with these symbols to be able to read and understand electrical schematics. In addition to symbols, schematics also use various lines and notations to indicate connections, voltage levels, and signal types. Solid lines typically represent conductors, while dashed lines may represent shielded cables or control signals. Voltage levels are often indicated by symbols such as positive, negative, and ground. Signal types may be indicated by labels such as AC, DC, or pulse. When reading an electrical schematic, it's important to start by identifying the major components and their functions. Then trace the connections between the components to understand how the circuit works. Pay attention to the voltage levels and signal types to understand the behavior of the circuit under different conditions. If you're troubleshooting a circuit, use the schematic to identify potential fault locations and to guide your testing procedures. Use a multimeter or other test equipment to measure voltages, currents, and resistances to verify the operation of the circuit. When creating an electrical schematic, it's important to follow established conventions and standards. Use clear and accurate symbols and notations, and label all components and connections. Organize the schematic in a logical and easy-to-understand manner. Use software tools such as AutoCAD Electrical or Eplan Electric Paint to create professional quality schematics. Electrical schematics are essential tools for anyone working with electrical equipment and systems. By understanding how to read and create schematics, you can improve your ability to design, analyze, troubleshoot, and maintain electrical circuits and systems. Let's also discuss some common electrical components. Understanding the function and characteristics of common electrical components is essential for working with electrical circuits and systems. Some of the most common electrical components include resistors, capacitors, inductors, diodes, transistors, and integrated circuits, or ICs. A resistor is a passive component that opposes the flow of electric current. It is used to limit current, divide voltage, and provide bias in circuits. Resistors are characterized by their resistance value, which is measured in ohms. The resistance value is typically indicated by color bands in the body of the resistor. A capacitor is a passive component that stores electrical energy in an electric field. It is used to filter signals, smooth voltage, and store energy for later use. Capacitors are characterized by their capacitance value, which is measured in farads. The capacitance value is typically indicated by markings on the body of the capacitor. An inductor is a passive component that stores electrical energy in a magnetic field. It is used to filter signals, tune circuits, and store energy for later use. Inductors are characterized by their inductance value, which is measured in henries. The inductance value is typically indicated by markings on the body of the inductor. A diode is a two-terminal semiconductor device that allows current to flow in only one direction. It is used to rectify AC voltage, protect circuits from overvoltage, and switch signals. Diodes are characterized by their forward voltage drop, reverse leakage current, and maximum forward current. A transistor is a three-terminal semiconductor device that can be used to amplify or switch electronic signals and electrical power. It is used in amplifiers, switches, and oscillators. Transistors are characterized by their current gain, voltage rating, and switching speed. An integrated circuit, or IC, is a complex electronic circuit that is fabricated on a single semiconductor chip. It contains thousands or millions of transistors, resistors, and other components. IC are used in a wide variety of applications, including microprocessors, memory chips, and amplifiers. IC are characterized by their function, pin count, and operating voltage. In addition to these basic components, there are many other types of electrical components, such as transformers, relays, switches, and fuses. A transformer is a passive component that transfers electrical energy from one circuit to another through electromagnetic induction. It is used to step up or step down voltage levels. A relay is an electromechanical switch that is controlled by an electrical signal. It is used to switch high-power circuits with low-power signals. A switch is a mechanical device that is used to open or close an electrical circuit. It is used to turn equipment on or off, select different modes of operation, and protect circuits from overcurrent. A fuse is a protective device that is designed to melt and open the circuit if the current exceeds a certain level. It is used to protect equipment from overcurrent and prevent fire hazards. Understanding the function and characteristics of these common electrical components is essential for anyone working with electrical circuits and systems. By selecting the appropriate components and connecting them correctly, you can create circuits that perform a wide variety of functions.